Hello everyone, Saulo Castro here. This is our fourth and last video in the series of rigid body kinematics. I know you are sad about it, but hold with me. For general planar motion, when we have rotation and translation simultaneously, we learned how to calculate the angular and linear velocities. We even learned how to determine the position of the instantaneous center of zero velocities, or IC. Now, it is time to learn how to calculate the accelerations for these cases. Also, in this video, I want to discuss more about kinematic constraints. The first thing that I want to start saying, and I will probably keep repeating this, is that for the accelerations, there is not such a thing as the instantaneous center of zero acceleration. Just in case you thought about it, it's a common confusion, but forget about this idea. The second thing I want to mention is that accelerations are not intuitive. In other words, I want to say that do never judge your results based on what you think it should be. Instead, make sure you understand your calculations and double check them whenever necessary. I will come back to these points later. The calculation of accelerations is of key importance while determining aircraft loads and also while calculating loads at different regions of the aircraft. These loads are needed for structural design and analysis, and also when you are determining the requirements for avionic equipment, for example. Imagine the aircraft shown in this picture, which has a given angular acceleration. Now you are working at a company, and your task is to design a new equipment, including the supporting structures. One of the equipment's requirements is to withstand the aircraft loads. How do you even start approaching this problem? Let's go through this quick example together. What is always our first step in dynamics? Yes, we start by defining a coordinate system. So now everyone knows what we are talking about. After that, we can draw our free body diagram of the equipment. Note how the forces replace the supporting points. Of course, that different supporting geometries will lead to different free body diagrams. And as an engineer, your task might be to determine the location of those supports. Now, we have finally our kinetic diagram containing the inertial forces according to our coordinate system. The accelerations that are used in the kinetic diagram, here named AX and AY, are calculated using rigid body kinematics. Knowing these accelerations will make possible to calculate the forces F1 and F2 of the free body diagram, and finally perform the required analysis for our equipment being designed. Now let's derive the equations that we need to calculate the accelerations at any point on rigid bodies undergoing general planar motion. Remember our flap mechanism. We looked into detail at the link OAB and how to calculate the velocity at any point B using the reference velocity at a given point A. You also learned the meaning of the relative velocity vector VB/A, which meant the component of the velocity at point B from the rotation of point B about point A. Imagine now a scenario with accelerations. We have now two angular accelerations, alpha and alpha AB, that must be taken into account in the analysis. Starting with our equations for the relative velocity, let's proceed differentiating the expression of VB with respect to time. The first differentiation leads to AB equals AA multiplying a more complex term. Let's now expand this differentiation. We see that the first term is the variation of the angular velocity with respect to time, vector product with RB/A. And the second term is the angular velocity vector product with the relative velocity vector. Thus, the expression for AB becomes the following. Note that the last term is a double vector product, which always leads to a vector pointing at the opposite direction of vector rb/a. Finally, we have arrived to the expression for the acceleration at point B. Evaluating these vector products, we can see that the first vector product represents a tangential acceleration, whereas the second one represents a relative acceleration that is always normal. Let's link this outcome with our previous knowledge on accelerations of rigid bodies undergoing rotation about a fixed axis. Applying the relative acceleration equation that we just derived to find the acceleration at point A using point O as a reference, we have the following. Remembering that point O is a fixed point, the acceleration there must be 0. Thus, the acceleration at point A becomes a tangential acceleration term added to a normal acceleration term. As in the case of velocities, while solving the accelerations in general planar motion, we should always start at the regions for which we know the accelerations and proceed towards the regions where we have more unknowns. In our flap mechanism, we should start by calculating the acceleration vector at point A, following with the calculation of the acceleration at point B. You have now all the tools to start working on problems involving general planar motion and accelerations. While solving these various problems that you encounter, kinematic constraints will appear, and it is worth dedicating some time in this video to talk about these constraints. Let's have a deeper look on how to include these constraints in the calculations. In this first example of a bar sliding, we have different constraints at point A and at point B. To start the discussion, let's define a convenient coordinate system. At the bar end denominated point A, we have only vertical motion, meaning that the velocity and acceleration vectors have only vertical components. These vectors can be written as shown here, according to our coordinate system. At the bar end given by point B, we have only horizontal motion, such that the velocity and acceleration vectors can be written as shown. Note that their magnitudes are unknown and we can calculate. The constraints have now been written in a form that is consistent with our coordinate system. Let's now solve for VB and AB. Using the instantaneous center of zero velocity, we can conveniently find the angular velocity of the bar at this given instant. Note that the angular velocity vector has a positive component in the z direction, according to the right-hand rule. Make sure that you understand this. The calculation of VB using the IC is very straightforward. I advise you now to pause the video and make sure you understand how I obtained omega and VB. To find the acceleration, let's write the relative acceleration equation in vector form. The relative position vector rb/a can be easily obtained. The vector product with the angular acceleration can also be solved. Using the unknown value of the angular acceleration alpha, the determinant leads to the following vector equation. Pause the video now and make sure you are able to calculate this vector product. Practicing whenever possible will always keep your algebra skills very sharp. Note that vector AB has only a horizontal component due to the kinematic constraints that we determined earlier. Thus, the vector equation becomes the following. There are two orthogonal components in this vector equality, which can be separated, leading to two independent equations. We have now two unknowns and two equations. Please pause the video and make sure you understand every step along the way. Quickly looking into this other example, we first define our coordinate system and we are then able to define the constraints in vector form. In this other example, we have constraints in a system where a gear rolls along a track without slipping. The non-slipping condition is applied at 2 points. First at point P, because we have contact between two gears, and also at point A, because we have an unwinding cord. First, we define a coordinate system. Then, we draw the kinematic diagram containing all relevant relative position vectors, velocities, and accelerations. We can now identify all kinematic constraints of this system. Starting at point P, the horizontal velocity must be the same of the track. The acceleration at point P was separated in a tangential acceleration, which must be the same of the track due to the non-slipping condition, and a normal acceleration, which depends on the angular velocity of the gear. Now, we can use the relative velocity and relative acceleration equations to continue solving this problem. This is the fundamental problem 16-22, and I will leave it as an exercise for you. Please pause the video and make sure you understand these constraints before continuing. Check now this other example, where at point C there is a constraint with an angle. Despite this might look complicated to some of you, we will now follow a procedure that breaks the problem down to simpler pieces. At first, we define a coordinate system, as always. Then, we follow by defining the kinetic quantities, or what we call a kinetic diagram of this system, indicating all the relative position vectors, the velocities, and the accelerations. Note that when the direction of the resultant acceleration vector is unknown, in this case the accelerations at point B are unknown, its components should be indicated. Here we have a tangential and a normal component. At point C, we know the direction of the velocity and acceleration due to the constraints, leading to the following equation. Finally, one should apply and solve the relative acceleration equations. Please keep this procedure in mind while solving rigid body planar motion. Moreover, start solving in the regions where you know the kinematic quantities for, and move towards the regions with more unknowns. In this case, we start solving at point A, we solve at point B, and finally solve at point C. In this video, we learned how to calculate accelerations in general rigid body planar motion. Also, we dedicated some extra time to talk about kinematic constraints and how they are considered while solving different problems. The intention of this video is to be your first contact with the new concept and to trigger your curiosity for the next learning activities. Please start right away reading the related sections and solving the recommended problems. With this habit and discipline, you will give yourself the chance to consolidate the concept very well. Goodbye for now, and I'm looking forward to seeing you in the next video or in the next lecture.